So let us understand the third law of thermodynamics. So the first law has inherent issues. What are the inherent issues? The energy can be transformed from one form to another. So energy can be converted into one form to another form. But really that will occur or not. So the spontaneity is not explained by second law of thermodynamics. The
Yeah, the
first law of
direction of heat flow also, sir.
First law of thermodynamics. That's what is direction of heat flow means.
Yes, sir.
So second law of thermodynamics made an attempt to explain in terms of enthalpy and entropy. That also failed. So again, I'm recapping. The spontaneity means without any external agency, external pressure, external force, external influence, the reaction should take place. So here reaction happens, diffusion. So gas is diffusion. Here initially you have the gases, right? Now here the gases naturally diffuses. It's a spontaneous process, okay, without any influence. Yeah. Now you can see the water is flowing. It is also natural process, right? Spontaneous. Higher level to lower level is spontaneous. Similarly, this spontaneous process are unidirectional and irreversible. Thermodynamics, we are not concerned with the rate, kinetics. Kinetics of the reaction, that is how fast is the reaction, how slow is the reaction, we are not worried about. We are worried about whether reaction will occur or not, right? So equilibrium reactions, whether the reaction involves equilibrium also, basically we'll come to know. So all natural processes are spontaneous. This is what is given by second law of thermodynamics. Now, enthalpy alone, enthalpy alone has failed in explaining the spontaneity of the process. So that's why another concept, entropy, has been introduced. So entropy means, you know very well, energy dispersal, disorder, or random state. Okay, highly disordered state. This is called entropy, random state. So this basically, entropy is a measure of molecular randomness. And the change in entropy, already we have discussed for isothermal process, adiabatic process, reversible and irreversible yesterday. And also entropy of mixing also you have learned. But by definition, it is delta S is equal to Q reversible by T. Yeah. So this entropy of the universe or total entropy is the summation of entropy of the system and entropy of the surroundings. So entropy of the universe or the total, if it is greater than 0, it is a spontaneous process. So if it is equal to 0, if it is less than 0, it is a non-spontaneous process. If it is equal to 0, the system is said to be in equilibrium. Yeah. So these are the things which you have learned yesterday in greater detail. Now, sign convections you have learned. Disorder is increasing, delta S is positive. Delta S is positive value. If disorder is decreasing, it is negative value. Now, examples you can see. A solid is converted into aqueous phase. definitely it is a disorder. So delta S will be positive, right? This is order state. Solid and liquid is a disorder state, and delta S has positive value. Similarly, H2 is a gas molecule. Those are converted into atoms. Naturally, it is more disorder. Okay. There is a disorder here. Both are gases. Disorder, there is a disorder. Because these are in atomic state, these are in molecular state. Yeah. Similarly, there is a decomposition reaction. So limestone is a solid, and you got a solid and a gas. And there is a mode energy dispersal. There is a mode disorder. This is the order state, and this is a disorder state. Delta S is positive. So delta S is positive is a good sign that reaction will be favored. Okay. Now you can see here in this system, 3 moles of gas is forming 0 moles of gas. So there is no here. Disorder is becoming order. So this reverse is happening. Disorderness is coming into order. So this is not favorable. Negative. So when delta S is negative, it is not a spontaneous process. Yeah. It is not a spontaneous process. Now, if you take NO and N2O4, both are gases. There 2 atoms are there. Here 6 atoms are there. So this is order and there is a disorder. So delta S is positive. So these are the things where, so enthalpy alone or entropy alone can't explain the spontaneity of the process. So already you know very well the basic thing. There is a randomness. So delta S is totally is greater than 0.
Spontaneous, sir. Spontaneous.
So it is a spontaneous process. Now, you know very well, heat cannot flow from a colder body to hotter body on its own. On its own, it cannot, right? All spontaneous process are thermodynamically irreversible and the entropy of the system increases. So it is impossible to construct a machine works in cycles and transfers heat from a low temperature to high temperature without intervention of external source. So these are the things which you have learned in second law of thermodynamics. Now, we are going to discuss, there is a need to explain properly the spontaneity of the process, and it was successful by using a new concept called Gibbs free energy, which is represented by delta G. So what is a state function? Again, state function means it depends on initial and final states. Now, I'm going to explain this Gibbs free energy in a simple way, actually. Now listen carefully. So Gibbs free energy uses both enthalpy and entropy. These two will be used. Now, listen carefully. This is called maximum work or useful work. This is total heat content of the system. Total heat. This is unavailable energy. and this is useful work, available energy. Now, how to understand this? I'll give a simple example. You just listen. You'll understand the Gibbs free energy effortlessly. For example, I take some food. So that is the total food. Total food is what? Delta H. Okay. Now that food is, what happens? It converts into energy. It converts into energy. A part of the energy is used to run this biological system, a body. Okay. To do the biological functions. Right? So that is unavailable energy. This is used to run the system. And remaining energy, I'm teaching you now. That is called, with that available energy, what I'm doing some useful work. What is the useful work? I'm teaching to you. Very simple. So a part of the energy is used by the system. That is unavailable energy. And what is the useful energy?
Delta G.
Which can be used by the system.
Which is not used by the system. The system will do
Yes.
some work.
Yes.
That is, delta G. Very simple. So when delta G is positive, negative, it is called spontaneous process. When delta G is positive, it is non-spontaneous process. We'll see all these cases. Okay. Now, H minus T delta S. Now listen carefully. Now, when it will be spontaneous, very simple. So H must be exothermic, right now? Exothermic means its value is negative or positive?
Negative.
Negative.
Negative, sir.
Negative.
Negative.
And
Less than zeros.
entropy should be more disorder. That means it should be
Positive. Sir.
positive.
Positive.
So this is the best combination. So delta H must be negative and delta S will be positive. Then delta G will be negative and it leads to spontaneity. Clear or not? So these are the better combinations. Clear or not? Yeah.
Yes,
So both enthalpy and entropy together can explain so spontaneity of the process. That is called Gibbs free energy. So Gibbs free energy is system to do useful work. So change in Gibbs free energy is delta G minus is equal to delta H minus T delta S. So these are also called Gibbs-Helmholtz equation. They are the scientist names. Gibbs is a scientist name. Now,
sir.
yes, please.
Sir, T is temperature, sir.
T is temperature.
Okay, sir.
We'll see all the possible combinations. Delta S is entropy. So total S is equal to delta S system plus delta S surroundings. Constant temperature and pressure. So heat content of the delta H is the heat content at constant pressure. Delta S, I'm giving the values of delta H. You know what is a delta H means? It is at
Enthalpy,
constant.
sir.
And delta S, Q reversible by T. Don't write Q reversible by T. Okay. So these are the surroundings. Already you studied this yesterday. So this is how it is derived actually. That's what it is shown. Okay. Delta H minus T delta S. This derivation is not required. So sign convection already told you delta S should be greater than 0, delta G will be negative. For non-spontaneous process, delta S will be less than 0 and the delta G will be positive. For equilibrium, delta S is equal to 0, delta G will be 0. So equilibrium values, delta G will be 0. Now, effect of temperature on spontaneity. Now, this chart is exceptionally important for competitive examinations. Now, let us see first one by one. Now, I'm going to write here. Delta G is equal to delta H minus T delta S. Now, if this is negative, this is positive, definitely G will be
Negative.
negative. G will be negative. 1 second. And it is a spontaneous process. Reaction is spontaneous at all temperatures. Now listen very carefully. Now it is negative. Delta S is negative.
Positive, sir.
Be careful.
Positive.
Listen
Positive,
carefully.
sir.
No, no, no.
Non-spontaneous.
Sir,
No, no.
we can't determine, sir.
No, listen carefully. Here temperature depends. Listen carefully. Now this is negative. Okay. Minus of T into this is negative. Agree or not? Agree or not?
Yes, sir. Yes, sir.
Yeah. Now listen carefully. When total will be negative, this is delta H should be more.
Delta H negative.
Temperature should be
Delta
low.
should be more, sir.
Temperature
sir.
should be low.
Yes, sir.
When temperature should be low, when it is low, this positive value will be less.
Yes, sir.
Yes, yes.
Positive value will be less.
Less.
Yeah. So low temperatures, will be favorable. Low temperatures is spontaneous. High temperatures is not spontaneous. High temperatures. See, listen. Both are negative. Delta G becomes positive at high temperatures. Be careful. So high temperatures, non-spontaneous. Clear or not?
Yes, sir. Yes, sir.
Yes, sir.
Yeah. Next. Now, these are all what reactions, exothermic reactions.
Yes, sir. Exothermic.
Yes, sir.
Now I'm going to explain endothermic reactions. Positive. This is positive. Okay. Delta S is positive. Then temperature should be high.
Yes, sir. To become
Yes, sir.
spontaneous.
Spontaneous. Understanding or not?
Yes,
If
sir.
this
Yes.
is
Yes, sir.
positive, if this is positive, if this is positive, then the T value is more, then negative value will be more. Clear? So positive. This is positive at low temperatures. That means reaction is non-spontaneous low temperature.
Non-spontaneous.
So high temperatures,
Spontaneous.
Non-spontaneous.
high temperatures spontaneous, you soup.
Yes, sir. Yes, sir.
Okay. Yeah. Now, next. If this is positive and negative, no chance. Non-spontaneous. All temperatures. All
Yes,
temperatures, reaction is non-spontaneous. So this is the crux of thermodynamics, third law. Clear or not? This table is very, very important. So it basically explains about the spontaneity under various conditions of enthalpy and entropy. Now, so I hope you understood. Same thing in a different format. Are you clear or not? Same thing only.
Yes, sir.
Yes, sir.
Yes, sir.
Same thing in a different format. Same thing. This is also same. Delta S is greater than 0. Exothermic. Any temperature, delta G is less than 0. Spontaneous. This is what, again, same thing only I put up in a different format. Now, one question. You have studied actually thermodynamics. This is already explained in chemical equilibrium. Chemical
Yes, sir.
equilibrium, I explained already. So, what I explained there, delta G is equal to delta G naught plus 2.303 RT log Q. Now listen carefully. When delta G is equal to 0, K is equal to Q, Q becomes K, equilibrium constant. So this is 0 is equal to delta G naught plus 2.303 RT log K. Now I can write delta G naught is equal to minus 2.303 RT log K. So this is the formula I used it. Am I clear?
Yes.
Check my notes.
Yes, sir.
Now here Kp value is given, T is given. Now substitute it. T, Kp value, you substitute, you get the answer. Clear? Yeah. You require Kp value and T value. That's it. Gibbs free energy is a what function?
State function, sir.
State function,
State
sir.
function.
It's extensive property or intensive property?
Extensive
it's
property.
extensive
Yes.
properties, sir.
Enthalpy, entropy, Gibbs free
Gibbs
energy.
free energy.
These are all extensive
Extensive,
properties.
sir.
Extensive property. So relation you know very well.
Yes, sir. Delta G equal to T minus T delta S dot.
Third one.
That's true. No, already equilibrium constant, already I did it just now. Okay. If you consider a reaction, which is equilibrium reaction. So this is the equilibrium coefficient.
Yes, sir.
So partial
Yes, sir.
pressures will be like this. Partial pressures. These partial pressures. So when reaction reaches equilibrium, so it reaches Q becomes equal to K. Agreed?
Yes, sir.
Then change in Gibbs free energy is given by this. This is the general formula. Just now I conveyed to you.
Yes, sir.
Then G is the random condition. This is random condition. This is the standard condition. 1 atmosphere pressure, 25 degrees. T is the temperature, R is the reaction coefficient. At equilibrium, delta G is equal to 0, Q is equal to K. Then naturally, substitute these values. Then you get this formula. Just now, we have done one numerical associated with this. So this is natural logarithm. When you want log, you write minus 2.303. Now listen carefully. K is greater than 1. Delta G becomes non-spontaneous. K is less than 1. K is less than 1, it is non-spontaneous. K must be greater than 1. Listen carefully. This value, listen carefully. This value must be greater than 1. Okay, then only delta G becomes negative. Then only it will be spontaneous. Always K should be greater than 1 for a spontaneous process. That is what you have learned. Na? K is greater than 1 means is forward reaction.
Yes, sir.
You
Yes.
already learned.
Yes, sir.
Yeah.
Sir,
Yes.
sir, here you told that K is less than 1, delta G is greater than 0, no, sir.
K is greater than 1. Forward
Yes,
reaction
sir.
when it happens. Listen.
Yes, sir.
K is less than 1 means backward reaction.
Yes, sir.
Forward reaction is spontaneous.
Yes,
K is
sir.
greater than 1.
K becomes 0 means then delta G becomes 0, no, sir. Log 1 is 0, no, sir.
K
It
is equal
can't
to
be
1.
1, no, sir.
Listen. K is equal to 1.
Yes, sir.
K is equal to 1 means equilibrium.
Yes, sir.
Okay. So already this is just a formula. Just now you have done it. Delta G naught is equal to minus 2.303 RT log K.
Yes, sir.
So this is the third law of thermodynamics. And now this ends actually thermodynamics. Of course, I have to solve some numericals. Numericals I have to solve. And entropy of a perfect crystal is 0 at absolute. It is 0
Zero, sir.
always. 0.
Zero.
That is, this is the third law of thermodynamics. Third law of thermodynamics is entropy of pure and perfect crystalline is 0 at absolute temperature. So thermochemistry. So I teach the basics now. So the last chapter, thermochemistry. So mostly other teachers also will complete the syllabus by this next weekend. So Lalit Chaitanya,
Yes, sir. Sir, is this a new chapter, sir?
continuation only.
Oh,
Thermodynamics, chemical
okay.
energetics.
Okay.
Chemical energetics consists of two parts, thermodynamics and thermochemistry.
Yes.
Now, first of all, I would like to explain. So what is in the thermochemistry? Thermochemistry involves enthalpy changes, enthalpy of formation, enthalpy of reaction, enthalpy of combustion, enthalpy of neutralization, enthalpy of solution, enthalpy of dilution, ionization enthalpy, bond energy, resonance energy, and so on. So we are going to learn all these things. Okay. Yeah. So enthalpy of formation. For example, water is formed. How water will be formed? From its respective elements like hydrogen and oxygen.
Oxygen.
So CH4 will be formed. It will form from carbon and hydrogen.
Hydrogen.
N2 will be formed. It will form from nitrogen and oxygen. So that is what is the standard enthalpy change for the formation of 1 mole of a compound from its elements in their standard state. So there is a lot of meaning in every word. Okay. First thing is, for example, if from hydrogen and oxygen, 2 moles of water is formed, that is not heat of formation. Heat of formation, by definition, only 1 mole will be formed. 1 mole will be formed. For example, I'll write here certain things. Let us see how many are going to answer this. I'm going to explain now. Carbon plus, I'm going to form ethanol, C2, okay, CH3OH. Let us take CH3OH. Now, is it heat of formation? Anybody?
Yes, sir.
Because 1 mole is formed.
Yes, sir.
This is not heat of formation because from its elements in their stable state. So hydrogen is dancing like this. Oxygen is available like this. So it is wrong.
Okay. So
So
directly means
yeah,
in the
carbon.
atmosphere like that.
Yeah. So
Okay.
now I'm writing 2H2 plus half O2 gives rise to CH3OH. Now is it right?
Yes, sir.
No, it is also wrong because the state is not represented. Okay. Now carbon plus 2H2 gas plus half O2 gas CH3OH. Is it right now?
No, sir.
No,
Why?
sir.
Why?
Sir, carbon state is not mentioned.
Okay, carbon solid.
Yes, sir.
No, it is also wrong. Because carbon can be diamond and graphite also. Na? So carbon, graphite, solid, plus 2H2 gas, plus half O2 gas, is raised to CH3OH. Is it right now?
Yes, sir.
Very,
Product state.
very good. Product is not given. Na? I didn't write product state. Solid plus 2H2 gas plus half O2 gas gives rise to CH3OH gas. Is it right now?
Yes,
Hmm?
sir.
Yes,
Yes,
sir.
sir.
It is also wrong.
Wrong, sir.
Methanol is in what state? Right? Soups. Methanol
Liquid.
is in what state?
Liquid.
Liquid.
Liquid state.
state. So H2 gas plus half O2 gas gives rise to CH3 OH liquid. Now it is it right?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
So see, now you understood heat of formation very well.
Yes,
Understood?
sir.
Yeah,
Yes, sir.
Yes, sir.
very good. H2 plus half O2 gives rise to water. For example, if you write vapor here, it is wrong.
Yes, sir.
So its heat of formation was this much energy. Now, listen carefully. What is the basic importance of what is a chemical equation? What is a thermochemical equation? Let us learn first. Okay, basics. So chemical reaction involves definitely energy changes, right? So thermochemical equation means some energy representation also will be there. So let us see step 1. Consider a reaction. Combustion of alcohol. Let us take this. Okay, step 1. Is it a thermochemical equation?
No, sir.
No, sir.
No. Let us see. Equation must be balanced first. Balance first properly. Balanced. Now it's a thermochemical equation.
No, sir.
No,
No,
sir.
sir.
Step 2. What do you have to write? Physical state.
We
You
need
write.
to write the
state,
state of everything.
Yeah. Now write this physical state. Clear? Yeah.
Yes, sir.
Now, is it a thermochemical equation?
No, sir.
No, sir.
No,
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 sir.
sir.
Why?
Because energy is not
That-
mentioned.
Yes, sir.
Yes. Yes. How much energy involved in this reaction is mentioned here. Now it's a thermochemical equation.
Yes, sir. Yes,
Yes,
sir.
sir.
Yes, sir.
You soups, listen. So step 3. Delta H will be positive or negative, you should write. Okay. So it is written
Negative. Sir.
negative, it is written. That is exothermic reaction. Okay. So this is a
Yes, sir.
thermochemical equation. This is a thermochemical equation now. Clear or not?
Yes, sir.
Yes, sir.
And if the reactant conditions are not mentioned, then the reaction happens at 298 Kelvin. That means this is H naught will come. Naught means what? Standard conditions.
Standard enthalpy.
Standard temperature.
Yes, standard. Okay. Yeah. So you know very well. Reverse reaction, if you write reverse reaction, what happens? This becomes positive.
Positive, sir.
Yes, sir. Positive.
This becomes positive. So these are the some of the things which you have to know. Are you clear or not?
Yes,
sir.
sir.
Yes,
Yeah.
sir.
Enthalpy of element is 0 in a standard state. For example, this is 0. Standard state. Hope you are clear. Yeah. So you learned how to represent a thermochemical equation today. Any doubts so far?
No, sir.
Clear? So tomorrow, so important class. I'm going to give a lot of definitions associated with thermochemistry. Any doubts, please? Thanks for bearing. Have a good day.
Thank you, sir.
Thank you, sir.
Yes, sir.
Thank you, sir. Thank you, sir.